Hello, everyone. My name is Keyvan Kasiri. I'm the applied AI researcher. Currently, I'm at Bank of Montreal as an AI researcher, and I've been working in financial domain for a couple of years. Here's the topic for my talk: machine learning in financial time series analysis. And my goal is to have an overview of application of machine learning and the definition of time series and its challenges in financial domain. Hopefully, we can have a good discussion after the talk as well. So to start with financial time series, well, time series is basically any sequence that has a notion of time, a time step, or it's not necessarily the real time that we in real life we deal with, but anything that we see a sequence step by step. And in finance, we can have actually a couple of examples, looking at, for example, transactional data that we can have in any debit card transaction, credit card, and they can be in multiple scales. Let's say in retail banking or commercial banking, they might be different in terms of their characteristic, but transactional data is a huge set of time series that are in finance. The other example could be market data such as stock market or any other market like any exchange markets. They deal over time. They work over time. As an example of the stock market, we can see, for example, S&P 500, and it has its different specific characteristics and behavior over time. So in this talk, as we move forward, I'm considering these two types of time series in finance, and I refer to these two to elaborate more on the features and characteristics. Time series, specifically in finance, they have specific characteristics. Stationarity is the first important feature, not necessarily the first one in terms of importance, but it's one of the most important ones. It means that the time series can be, it is time dependent, and the time dependency can be in different, can be sensed in different momentums. It can be when you look at the mean of the signal, when you look at standard deviation or other momentums of the signal. We can see that in market data and transactional data, and the stationarity is very different from one type to another type. For example, in high frequency data, you will see non-stationarity in very high frequency. And all other example could be transactional data that, for example, in retail banking, we don't have that high non-stationarity and that dynamic behavior compared to market data. And also, if we move to commercial transactional data, since there is not as many detailed noisy transactions, we can see less non-stationarity there. And also, there are seasonalities in time series, in financial time series, which is inherited from the nature of economy. As we see in market data and transactional data, normally at the end of the year, at the end of each fiscal year, and there are also certain times over month or days that we see specific behavior happening. Also, the other feature is conditional dependency, and this is general to all time series. That at each time step we have dependency to the previous steps. It could be very long in history. It could be very efficient in terms of the number of steps that we go back, and it also differs from one to another. We also have interchannel dependency. What it means is that let's open it up with examples. For example, for transactional data, a client can have multiple accounts, and these accounts, the behavior in the different accounts can be highly intercorrelated. Also, in market data, we can see this effect as we see different behaviors. We can see same behaviors in data related to the same industry or to the same in the same market. So these inter-channel dependencies should be also considered when we are analyzing data. Noise has a very broad definition, and it highly depends on what we want to do with the data, with financial data. It could be outlier removal or outliers in the signal. It could be the long tail in distribution of data, or any other types of undesirable effects in data. It could come from the method of capturing data that cause a lot of missing points or wrong labeling or wrong flagging. These are all noise, and it depends what we want to do with the signal, with the data. So at the end, the question is what we want to do. What is desired for us? Is it for forecasting, for example? Do you want to model the distribution of data, or is there anything else? As we move forward, the first step in dealing with time series in finance is, in ML perspective, is to look into different components of the problem. Input is the first part, where we need to select we have to have the right selection of input in terms of features, in terms of source of data, and also size of data. This is very important when we are building an ML pipeline for financial time series, because we need to deal with the long history probably, or we need to deal with a large number of samples for training our models. So this is a very important factor. And pre-processing, as I discussed, all these denoising, any preparation before entering the model. It could include variety of methods. Modeling is the part that mainly deals with nonlinearity in the signal and dynamics of this time series data over time. And the last part is definition of target. What we want to do with the target, with the data, what should be the criteria to evaluate and to actually design the model. The model should forecast the trend or event, or it should model the sequence distribution. It should model the noise. It should extract the noise. The criteria to build this model, and also the criteria to evaluate the quality of the outcome should be defined as well. Looking deeper into feature, traditionally feature engineering has been done on financial data and other types of time series. When you look at financial time series, there are a lot of similarity with other time series like biological signals as well, but there are certain differences in pre-processing and feature engineering. We can see these differences, depending on our requirement. The first thing is normalization or standardization. This is a very common practice to do normalization and standardization. Most of the ML methods have the work best on the data that is following normal distribution. So normalization is putting a huge assumption here that we should map our data to a normal distribution, but it's not necessarily the case that we can do at this point. Standardization has a very more general meaning here, and there are multiple methods already proposed for standardization. I will go through that as we move forward. The other thing is outlier removal. If you look at the figure on the right, this shows the daily account balance for 2 years for a specific account. This is a generated signal to show that, and we see, for example, we have a huge outlier, a huge spike, and if we look at the histogram of that account, it shows those spikes, those huge changes in the signal is shown as a long tail in the distribution. So this outlier is another concept for feature engineering. The rest of feature engineering mostly is tied to time concept of the data, which we can actually consider the stationarity of the signal in different scales, using rolling windows as trying to make non-stationarity to stationarity, with the determination of a specific window size or definition of a scale and time domain. And most algorithms in ML are not scale and shift invariant, so we have to be careful about shifting and scaling when we are doing normalization and standardization. Looking at the models, traditionally ML models, that are dealing with time series are autoregressive models, Kalman filters, and the major drawback is that they're mostly univariate. They cannot deal with multivariate. Definitely there are multivariate versions of them, but I'm talking about the common methods. And also there a lot of linearity is involved there. And for that reason, they hugely rely on feature engineering. Modern approaches based on neural networks are proposed in these past few years based on RNNs and CNNs. These two major categories are used for modeling the financial time series as well, as in other domains in machine learning. Moving forward, the challenges with financial data, which is the main part of this presentation. The first thing is, I mentioned standardization. Scaling is, and mean max scaling and standard deviation mean scaling. These are very common practices to standardize the signal. But as we see, these scaling methods are not able to deal with spikes in the data or the long tail distribution, and actually if we have a huge outlier, it's making the rest of the data insignificant. Moving average is performed way better than the rest of standardization methods. Simple moving average, weighted, and exponential moving averages are the ones that are actually in practice. And if we want to actually look at the figures at the right, we have the time series for 2 years of transactional data, bottom left, and its histogram. We see that top left and then top right, the histogram. The bottom left shows the red signal, which is the output of a simple moving average. We see the behavior signal is still there. We're not suppressing anything in the signal, but the huge spikes and changes in short period of time are smoothened. And in the bottom right, different approaches for moving average, simple moving average, weighted moving average, and exponential moving average are shown in a very zoomed in part of the data. If we have 5 different steps in our data, we see that how smoothing is happening with these different approaches. We see, for example, exponential moving average well, we can, with this exponential moving average and with very appropriate parameters, we can have proper smoothing uh, without actually changing anything in the behavior of data. Moving forward, when we are dealing with huge outliers, we need to do nonlinear mapping as well. Something without suppressing the rest of the signal. If we look at the example in top left, this could be an original time series with a huge spike, which is obviously a very significant outlier that can change everything in the behavior of a model, and a model cannot easily deal with these types of outliers. If we look at the histogram, we see a very long tail, and at the end of the tail, we see the effect of the spike. Some nonlinear mappings, tangent hyperbolic, they can actually scale the signal while they're they're mapping the huge spikes to the rest of the signal, and keeps the top and the bottom of the range constant. So if we look at the nonlinearly mapped signal on the left bottom, we see we actually magnified the small changes in this in the data where the spike has been removed, and nothing else in the overall behavior has changed. That only this part has been mapped, has been decreased to be in the range of the rest of the data. And if you look at the histogram, it's mapping the histogram of data to something closer to a more flat distribution. So basically, the long tail is removed from the histogram. Moving forward with the other challenges in financial data, there is a very important factor here, a very important concept of synchronous or asynchronous data, which could be in input data or the model output. Looking at the example in transactional data, the ones that are in the box, we saw, for example, we have 2 transactions happen in one day, but the rest of the transactions are in other days, and the time difference are not constant. So this asynchronous behavior is actually making it more difficult to build a model that understands time. If we want to have a more one-to-one mapping with time steps, we need to actually let the model understand the difference in between each timestamp as well. So there are cases where we need asynchronous input data with regular time steps. So we need to add features to let the model know about the time steps. Or also, the model can deal with the asynchronous data and generate asynchronous output as well. So when we have asynchronous output, we need to understand how we want to actually deal with this asynchronous output to generate the final the final output of the whole ML pipeline. So it could be meaningful. For example, in a stock market, if we have a stock and the trades are the orders and trades are happening asynchronously, which is actually happening in data in the market, then producing the prediction for that, we cannot necessarily produce the prediction for the next order, because we don't know when the next order is coming. what we can do, we can actually put a limit on the window in future, or we can predict the behavior of next change. Those kind of things, we have to be careful about this asynchronous or synchronous concept here. There's also another challenge with long-term and short-term dependency here. Well, RNNs, different RNNs have been designed to deal with short-term and long-term sequences. But the most important part is we need to understand the nature of data. Do we really care about the long-term history? How the output is dependent on the history? So those kind of things we need to know beforehand, before designing the model and setting the parameters for the model. The model cannot understand it automatically that what dependency it should look at, and also depends on the frequency, the concept of frequency in data. There are cases where we need to look into multiple scales of frequency, and then let the model know about the proper frequency. So there is another thing. I'm going to wrap it up in the next few minutes. This is inter-channel cross correlation. So looking at the best example is stock market. We have multiple stocks in one industry, and we see, for example, in tech industry, all the stocks are moving together. This is also the same for transactional data. If you have multiple accounts, your overall financial situation will affect all these accounts simultaneously. The details might be different. The types of usages that you have for your accounts are different, but overall, if you're getting into a wealthy situation, it will be shown in all your accounts. Or if you're getting into a bankruptcy situation, all your accounts will obviously show those effects. So these cross correlations in the accounts or in the markets, these are something that over time it needs to be considered as well. So each of these inputs each of these nodes basically are connected nodes that move together over time. Their response over time might be different. This should be considered, but there is connection between these different nodes. And how the question is how to group these time series together for accounts. We know that, for example, we know a client to have multiple accounts. This is easy, but for something like stocks or other types of time series, we can rely on the overall reports that defines the industries or groups of stocks and markets, or we can go through clustering methods, and then based on those clusterings, learn the embeddings for each group, and then use those embeddings in our learning for doing forecasting or any model. Overall, I try to have an overview of challenges of using machine learning in financial data. I hope it could be useful for everybody. But what I tried to cover was the major examples in market and time and transactional data, and usage of ML overall approaches in dealing with time series problems, and highlighting the challenges in financial time series. Would be happy to answer if there is any specific questions.